Hello, my name is Ian Fogarty, and I'd like to talk to you today about the concentration of H+, OH-, pH, and POH. A couple of videos ago, we had already talked about the autodissociation of water and Le Chatelier's principle. So I'd like to take just a few moments and review that ever so quickly. So here we have water, and it can split up into H+ and OH- according to Arrhenius. The Bronsted-Lowry version is a little bit different, but Arrhenius will work for us today. And so the Kw is equal to the concentration of H+, OH-, and that will equal 1.0 times 10 to the negative 14. And if you remember, Le Chatelier's principle says that a system in equilibrium will shift in a direction so as to minimize the effect of any stress. Normally water splits up and you have equal amounts of H+ and OH-. However, if I do something to change these, suppose I were to increase the concentration of H+, what would happen is that means there's more H pluses around for the OHs to bump into, and so then the hydroxide would have a better chance of picking up a proton and going backwards and forming water. And so that would mean that the concentration of hydroxide would go down. The concentration of H+ would go down a little bit, but not enough to counteract what was happened to it. And so then this number would be a little high, this number would be a little low, and together they would still equal that. If you had an acid like HClO, it would split up into H+ and ClO-. Now it's only a weak acid, and so it's not going to split up 100%, so that's why we have the equilibrium. So if I filled the icebox, the concentration at the start of HClO would be perhaps 0.1. The concentration of H+ at the start would be 1.0 times 10 to the negative 7, because that's from the regular water split up. And then this hasn't split up at all. This reaction hasn't occurred yet, and so there's 0 of those. And then when we press play on the reaction and allow this reaction to actually come to equilibrium, we're going to lose some of this, and we're going to gain some there, and we're going to gain some there, and we end up with 0.1 minus x, and x plus a very small amount, 1.0 times 10 to the negative 7, and x. And then we could take those numbers and put them into our Ka and find the concentration of H+. And I don't want to spend much time here. We've already talked about this in some detail. As time goes by, depending on the concentration here of the acid and the Ka value, this x could be big or small. And that's really what I want to talk about. What is the concentration of H+ in these reactions? Sometimes they're huge and sometimes they're tiny. It's really the concentration of H+ that I want to spend some time on. And so we have a variety of concentrations here, from 1.0 times 10 to the negative 1, or maybe easier, 0.1. all the way down to 2.0 times 10 to the negative 9, 0.0000, a whole bunch of zeros, 8 zeros, and then a 2. And if that looks like a lot of zeros, it's really not. We could have as many as 13 zeros there in the range of H pluses. So most of the time, when we look at a number, we would say that, wow, we've got a whole bunch of zeros here and then a 1. We've got the same number of zeros here and a 2. This is twice as concentrated as that. And that would be a significant thing. And it's true, it is twice as concentrated. However, when the range can go from 0.1 and even larger than that, all the way down to 2.0 times 10 to the negative 9 and down to the negative 14s, maybe this number isn't so important. Maybe it's the decimal point that's important. Whether this number right here is a 1 or a 2 or a 5, maybe that's not the crucial piece. Maybe the crucial piece is the fact that there's a number in the third decimal point. And maybe the fact that this is a 1 or a 2 or a 9 isn't so important. It's how many zeros come ahead of it. And so because of this, because there's such a large range, and going from here to here, although it's doubling, isn't really that big of a change compared to what's possible, we need to try and come up with a new scale. pH is equal to the negative log of the concentration of H+. So maybe, if I'm looking at scientific notation, maybe this number, which corresponds to that number, isn't the important thing. and there we're doubled. Maybe it's that number, the exponent, that is the important thing. If we run this through our equation, we would have, let's pick on this guy right here. We would have the negative log of 1.0 times 10 to the minus 9, and then that, the log of that would be negative 9, and then the negative in front of that. What this says is the concentration of H plus really is a 1 with 9 zeros in front of it. We get a pH of 9. If we do that for all the other ones, we're going to have this number right here. The power of that is going to be 1, and then if we get rid of the negative sign to match that negative sign there, then we end up with a pH of 1. And likewise 3, and then 9. Now this is twice as concentrated, but the power isn't going to change. So it's going to be a little closer to 10 times 10 to the negative 8 than it is 10 times 10 to the negative 9. So it changes ever so slightly because of that number right there. As you can see, the pH here is 9 and it's got lots of zeros. The pH here is 1 and it's got only 1 decimal point. That's going to be a little weird for us at first because we're used to large numbers meaning a lot. And so if we think about the way we normally think about our numbers, we would say, oh well, if pH has something to do with concentration of H plus, and that's a big number, 9, then there would be lots of H plus here, and that's a small number, 1, it must have a little bit of H plus. That's kind of the way that we normally think, but that's not true. Because it's the negative exponent, a pH of 1 actually means there's a lot of H plus, and a large pH means that there's a lot of zeros in front of them, and so that's actually a small concentration. And so a larger pH means you have a small concentration of H plus. It's a little bit counterintuitive for us. And so we have a scale, and normally we think of the scales going from 14 down to 0, but that's not actually true. It can be a little bigger than 0. You can have negative numbers. Those are really acidic. And so, but normally we think of 14 to 0, with the center being 7 as neutral. And so at a pH of 0, there it's very acidic. There's lots of H pluses. The concentration is high, and because of Le Chatelier's principle, the concentration of OH minus is really low. When we're pH 7, it's neutral, so the concentration of H plus, is equal to the concentration of OH minus, which just happens to be 1.0 times 10 to the negative 7. And then at a pH of 14, it's very basic. The concentration of OH minus is really high, and the concentration of H plus is really low. We also have this thing called POH. Whatever we can do with H pluses, we can also do with OH minus, and so this POH is exactly the same thing, it's just the opposite. And so here's our formulas that we have to work with. KW is equal to the concentration of H plus and OH minus is equal to 1.0 times 10 to the negative 14. So if one goes up, the other one has to go down, so that number stays the same. pH is equal to the negative log of concentration of H plus. POH is equal to the negative log of concentration of OH minus, and the pH plus the POH has got to equal 14. We can use those to do some math. What is the concentration of OH minus in a solution where the H plus is that? So I'm going to go from here to here. Well, the formula I'd want to use for that would be KW is equal to the concentration of H plus times the concentration of OH minus, which is equal to 1.0 times 10 to the negative 14. So then I would put in 1.6 times 10 to the negative 5. Concentration of OH minus is what I'm looking for. So the concentration of OH minus is going to be 1.0 times 10 to the negative 14 all divided by 1.6 times 10 to the negative 5. Then I run that through my calculator, and I end up with 6.25 times 10 to the negative 10. So the concentration is fairly large here, and so together it's going to be a pretty small. Well, let's go from here to there. So the pH is equal to the negative log of the concentration of H plus. And so pH is equal to the negative log of 1.6 times 10 to negative 5. And I know before I put in my calculator that it's going to be somewhere around 5. Maybe it'll be a little less, maybe it'll be like 4.9 or 4.8, but it's going to be somewhere around that negative 5. So I throw that into my calculator, and out comes my answer, and the answer turns out to be 4.8. To calculate the POH, I have some choices. To calculate the pH, I could go from here to here, or I could go from here to here. I think I'll try the red one for right now. So pH plus POH is equal to 14, and so 4.8 plus the POH is equal to 14, pH is equal to 14 minus 4.8, and so the answer turns out to be 9.2. Great. However, I could have also gone the blue way, and so POH is equal to the negative log concentration of OH minus, and so POH is equal to the negative log of 6.25 times 10 to the negative 10. And then the POH turns out to be negative 9.2, and that's 9.2. So in this question is similar but different. It's just going backwards, and I could go this way using the POH formula, and pH plus POH is equal to 14, and I could do that and get a nice answer, but I'm going to choose not to because the math is a little simpler and I want to do a different way and practice some different math. So I'm going to do things slightly different. Instead, I'm going to go from here. I'm going to go from here to there. And so my POH is equal to the negative log of the concentration of OH minus 12.5 is equal to the negative log of concentration of OH minus. And so I'm going to bring the negative over, multiply both sides by negative 1, so it's going to be negative 12.5 is equal to the log of concentration of OH minus. And so when I divide over here, I'm going to multiply on that side. When I add on this side, I want to subtract on that side. What do I do when I want to get rid of a log? Well, that's going to be 10 to the x. So 10 to the minus 12.5 is equal to the concentration of OH minus. And so then I type that into my calculator, looking for the 10 to the x button. And if I do that, I end up with 3.16 times 10 to the negative 13. Now that I'm at the concentration of OH minus, I want to go this way and practice my KW formula. And so my concentration of H plus will equal 1.0 times 10 to the negative 14 divided by 3.16 times 10 to the negative 13. So that's a really small concentration. So this is going to be pretty large. And that's pretty large. Now if I want to find the POH, I have some choices. I could go from here to here, and that would be the easiest one. But again, I'm trying to practice some math here. So I'll use something to go from here to here. And so the pH is equal to the negative log concentration of H plus, the negative log of 0.0316, which is really something times 10 to the negative 2, right? 2 decimal points. So I'm expecting something around 2-ish. And so I throw that in my calculator, and out it comes. And 1.5 is reasonable. Thank you very much for your time.